Thank you very much. In Linaro, for the HPC SIG, one of the missions is to validate the whole ARM ecosystem, HPC ecosystem, and for that we need to build a lab. So this validation goes through what we call a validation matrix, and this matrix aggregates tests, and this matrix is applied in our lab, and this lab aggregates many machines, all of them in the same infrastructure, in the same physical place, and so we apply this validation matrix. The validation matrix must be applicable to every machine. This is very important because we have to have the same base of tests to compare them. And the validation matrix's dimensions are the different software configurations that we can have in an HPC environment. Of course, we need to take that matrix and to generate as few tests as possible, to have a CI loop that goes as quickly as fast as possible. Um, all of that without losing information. This is critical. So the infrastructure has different needs. It needs to dispatch jobs, HPC jobs, of course, but the tests in themselves, the provisioning of each of the clusters in the machines, and the compiler benchmarks for for compiler performance. Um, this goes through providing DHCP TFTP services for provisioning. This goes through package cache as well because we need to have the same version of packages to compare them efficiently between the machines, of course, to have the same environment. We need to provide a secure file and results storage service because those tests could be used to compare machines, and that cannot be done by Huawei assignees to compare with Qualcomm machines and Qualcomm to compare with Huawei. We want to have a private and secure space. Of course, be low maintenance. We do not want to spend that much time on the infrastructure in itself, and be able to be replicated anywhere else. This this is because this is a scientific process, so we need to be able to replicate this anywhere, and anybody could be um, could take what we've done and do it in his own infrastructure, in his own laboratory, and to see if he reaches the same conclusions and results as we did. So um, this infrastructure can be uh, represented here. So we have a vertical slice of the stack. Um, the main components of this vertical slice is the application, of course, um, the HPC environment stack with all the libraries, binaries, and compilers and that are involved with the infrastructure, and the underlying operating system, kernel, and network and drivers and all of that. That is that that the HPC stack needs, and as extras outside of this stack, we have InfiniBand, Lustre, BGFS support, which is all very important for the HPC ecosystem. It is um, it is not mandatory to perform these tests. Um, it is, of course, part of the validation matrix, but um, as a basis, we do not need them. So in our lab, the HPC stack, we take it from OpenHPC um, to have one basis. It is open source. And the main validation application that we use is the OpenHPC's own test suite. So it allows us to have the same basis, the same validation application for all the clusters that we have. So all of that, we need to simplify this, to simplify the validation matrix to reach the least amount of tests required. So we're going to strip it out of the extras in the application and we're going to concentrate on the provisioning. So the provisioning, we have the network, the kernel, the operating system, and the HPC stack. But provision this, we have multiple ways of doing this. We have the stateless, the stateful. We could do it directly via SSH and Sybil, or we could do it via Werewolf or XCAT. Those are dimensions to the provisioning axes of the matrix. So as we can see there, the process is repeated for Werewolf stateful, Werewolf stateless, and Ansible, which is stateful. So those are different test cases, right? Different use cases. Then we have to worry about network layouts because, for example, Werewolf stateless implies an internal network with an internal DHCP running on it. And whereas if we have a flat network, we can do Ansible uh, with only one DHCP for all the clusters. Um, and then we have different kernels, of course, because some of the machines in our lab uh, um, needed some patches that were not upstream yet. So we have the ERP kernel, Enterprise Reference Platform, which is distributed by Linaro source, of course, which contains patches that are being in the process of being upstreamed or will not be upstreamed because um, they contain support for microarchitectures uh, that that are not yet upstreamed. Um, and of course, the upstream kernel, which is the upstream for the distribution that we use. So upstream for CentOS 7.6 ARM, so that's the 414, and um, and on Debian. So we have an OpenSUSE, of course. So we have above that the operating system. Sorry. So we have three available to the user: Debian, which is primarily used for benchmarking; CentOS, that we use to install the HPC stack for; and SUSE, the latest one, which is in the process of being integrated in the OpenHPC recipes, installation recipes. There is no Debian support on or OpenHPC um, because all the packages are RPMs based and no. So we take uh, this complicated slice of this complicated representation of the validation matrix and we try to simplify it. So if we take um, the network, it is invisible to the user. The user doesn't care about it. It's handled by the installer itself, by its scripts, and it relies on the hardware configuration, how you plugged in the cables in the switch, of course. Next, provisioning. Provisioning, although dependent on the network layout, um, you can get bundle the kernel and the OS and um, and have and allow for multiple ways of provisioning to coexist together. So, for example, we could very well install a cluster using Ansible, all stateful, and another cluster using Werewolf stateful, um, stateless. Sorry, so VNFS. Um, the application environment um, is we do need to have control over how we configure the OpenHPC stack. And this also relies upon a common operating system configuration among all the clusters and all the different configurations. Um, Idempotency, potency, of course, because you want to be able to rerun the installation process on an already installed cluster if you ever want to modify some configuration without reprovisioning the OS, without wiping the slate and getting and starting from fresh. Um, Package caches, as I've mentioned before, it is very important to rely upon versions of the packages that you know are there and are fixed. And especially since we are working upstream, if OpenHPC um, upgrades version and some packages are deleted and the configuration doesn't work, we still want to be able to have a configuration that works. So this package caches allows us to fall back on the previous version of OpenHPC and and thus still keep the lab running. Um, and of course, there's this extra part. Um, so this extra part is integrated into the main recipe and features InfiniBand support, so how to install it, whether it be the Mellanox OFED or the open source drivers, uh, Lustre server support, which will come, and future additional features. So that accounts for additional hardware, BGFS support, and all those kind of features that you could say are extras. Well, not the whole stack does not depend strictly upon them. So we reach a simplified slice, and whereas we have three elements that the user can configure. So we have the provisioning, we have the environment, and we have the extras. And on top of that sits the application that the user wants to run. So there are two use cases. Either the user just wants to run the application without further configuration. So he just tells the Jenkins to run the application, and then it takes the default configuration for that kind of application. And if the user can also go a little more further into the details and fine tune everything in the environment as much as possible. So that is for what we want to do. So what have we been? What is the status on all of those things? So from a strictly provisioning standpoint, a cluster deployment. Um, so far we have been using Ansible stateful on all the ARM clusters. It works perfectly. And then we have on top of that the OpenHPC installation recipe has been developed with the collaboration of Fujitsu. And Werewolf has been manually tested, so it is not automated yet, but it does work. And what are we doing right now is trying to get Werewolf into the recipe, into the automation, and so as to have the option to either Ansible stateful or Werewolf stateless. And then next, we will try to enable Lustre on the Lustre as a on ARM, so client Lustre client on ARM using an Intel machine as the server. Concerning the enablement of applications, so far we've been using the Open HPC test suite and using enabling all the tests that were running out of the box, meaning without fine tuning the environment, just running the test suite, those enabled, it worked. So what we're doing right now is trying to enable the test that we know should be working on ARM, but we need to fine tune the configuration for that. And in the future, we plan on running other applications to validate the deployment and maybe go beyond OpenHPC to look for those. Uh, Concerning toolchain benchmarking, so far we've have an automated run of the benchmarks using a benchmark harness is as generic as possible, and this can run as well on our machine as well as Intel machines. Um, it runs as of now Imeno, Lulesh, and OpenBLAS benchmarks, and um, fetches them, compiles them, runs them, and gets back the results. What we're trying to do right now is, of course, add more benchmarks, but further the analysis on those on the results that we get. So to have a proper statistical analysis of the results. Of course, we try to reduce noise um, by setting the environment, by configuring the environment very precisely. Um, Next, of course, we will automate all this benchmark running to have a continuous run of the benchmarks, so as to constantly feed the statistical analysis with the results. Um, and eventually reach a point where we can develop a tool to assist in toolchain comparison using all those uh, results, statistical analysis on those results to do this comparison tool. And so we've also been working, of course, on libraries, uh, enablement on ARM and enhancement on ARM hardware. So far we've been working on OpenBLAS. So OpenBLAS has been validated and patched to build as efficiently as possible on all machines that are available to us, that are in our lab. Um, we've been using perf test to benchmark MPI. Um, what we're doing right now is to further optimize the build options per microarchitecture, per ARM microarchitecture. And on the MPI side, what we would like to do is have an automated run of the MTT test. Um, Next, in the future, we want to enable dynamic architectures for OpenBLAS and eventually uh, validate LMP. So the future for the HPC SIG ecosystem validation um, is means that it's very important for vendors to rely on Linaro for base open source software validation, because we have multiple vendors available to us, multiple type of microarchitectures, and we have a standardized infrastructure to do it. Of course, that does not mean that the vendors cannot run the same infrastructure as we do, and we can then compare results. Um, we want to share our work as well, especially the OpenHPC Ansible recipes that are being developed with collaboration with Fujitsu, and we want to upstream them and make them available and supported as well by the OpenHPC community. Our software-defined infrastructure, um, we make it public, and we want other people, other members, to replicate our work and to point to areas that need further enhancement or suggestions. Um, have a community continuous integration. So with all the different validation applications I've talked about and different benchmarks and tests um, to do to validate all the things, whether it be MPI, OpenMP, OpenBLAS, OpenHPC, and other things. Um, we want to allow our engineers to develop the ecosystem as well. So uh, by abstracting all the infrastructure and all the complicated configuration that is needed, we can empower um, engineers that are not well versed into Jenkins or any of the Ansible is running in the background, and just concentrate on the tests, the benchmark, the results, and how to further enhance all of that. Of course, the infrastructure must allow us to test new packages, libraries, compilers, and compare them all, and be able to have statistical analysis and um, in-depth analysis of all those results, and to allow us to further enhance and optimize everything. And so uh, the HPC lab setup, which is the the main repo containing all the setting up of the infrastructure, is there. So it's on GitHub. It's public, of course. And the Ansible OpenHPC installation recipe I've talked about, developed collaboration with Fujitsu, is also available publicly on Linaro's GitHub. And um, that pretty much concludes uh, the ecosystem validation presentation. If there are any questions.
There's a lot of work about in this ecosystem, especially if you go into the open HPC repository. There's plenty of things to do. So I'm wondering what a strategy to reduce this kind of effort workloads.
We try to coordinate with each of the actors involved in the OpenHPC community so as not to step on each other's toes. And uh, we have some dedicated areas of work. For example, compiler benchmarking, especially OpenBLAS, has been, like I mentioned, a focus. And in general, uh, at the moment, we've been focusing on the installation process and being able to easily get the stack on our software. And then once we have um, a stable way, a way that is being able to be replicated easily, then we have a base, uh, a solid base to work further with everyone on OpenHPC's optimization and enhancement on our hardware.
Thank you.